Alrighty, yabba dabba dabba doo. Let's take a look at what we call relative numbers here. Let's take our pale blue dot, as Carl Sagan called it. I'll make the Earth right there. And we've got our little celestial brother way out here. Oh, sister, actually. It's Selene, goddess of the moon. And that's the moon. And occasionally we have these asteroids passing close to Earth. And the question is, how close did it get to Earth? Okay? And so rather than trying to get the public to understand these distances, instead what they do is something like this. This is the distance from the Earth to the moon. And we would call this a lunar distance. Like that. 2 seconds for light to travel. We could give it a name, lunar distance. And it tells you how far the Earth is from the moon. It has a meaning in kilometers, it has value, but we don't care. We use this as a benchmark, a meter stick. So let's say some nasty old asteroid comes peeking at Earth. It gets a little too close for our comfort. And NASA wants to convince the public that this was a fairly near miss. So instead of saying it was 5 million kilometers away or something like that, they might report it this way. They would say, well, look, for all you folks that don't think that that was a close call, if that's the distance from the Earth to the moon, this nasty killer asteroid was only 2.5 lunar distances further away. 2.5 times further than the moon is. And this is a way of making it relative, because even if you tell people the actual kilometerage from the Earth to the moon, the number's too big to make sense. But when you're standing on Earth and you look at the moon in the sky and you go, this asteroid showed up only 2.5 times further away than the moon is, then people might go, oh, that's kind of scary. What's been the closest approach? Oh, I'm not sure you really want to know. Less than half of a lunar distance away. So this is a way of making numbers relative. We can do the same thing with the Earth to the Sun. My colorblind eyes, I can't see it now. Where did it go? Where's my mouse? Let's see. No, that's not quite where I want it. Let's try again. Again, I can't do all my lessons as professionally as I would like because there's just too much for me to convert. So I do try my best, but this one's fine. It'll work. So let's take the distance from the Earth to the Sun. That's about 150 million kilometers. And we want to get an idea of how far away another planet is. Say, oh, Mr. Clown Pants, Jupiter. Mr. Clown Pants, Jupiter looks like it's got clown pants. And it's got that, no, it's the same color to my eyes. It's not clown pants at all. There we go. And you want to know how far away Jupiter is. Well, I could give it to you in kilometers, but what if I instead said Jupiter is 7 times further away from the Sun than we are? We set this to be our meter stick, and we call this distance from the Sun to the Earth an astronomical unit. You know when people say, that's astronomical, I'm not paying that. Well, astronomical unit actually means 150 million kilometers. So this is one of the relative numbers that we use occasionally because, you know what, it's a lot easier to say Neptune is like 17 further times away from the Sun than we are, rather than it's 1819763, you know. It's just a way of making things relative, and you can convert later. Now, the nice thing about relative numbers is their ratios don't change for mathematics. And I can show you that in a different setup. So we're going to switch screens. I'll have to pause this. What do I mean that relative numbers preserve ratios? What if I have a mountain that's, say, 1,500 meters tall? And there's another mountain that is 150 meters tall. And I want to make a scale model of them. I'm going to make a scale model, but I'm going to use a relative size. I'm going to set my base value is insert special character division. There it is. Insert it once. I'll go over here. I'll insert it again. And I'll get rid of that. And I'm going to go divided by 150. So my shorter mountain becomes my benchmark, my number 1. My second mountain becomes 10. These are in meters. These are no longer have any units because both of these divided by meters. This is size 1. This is 10 times bigger, not 10 meters bigger. What's the height difference between these two mountains? It's 1,350 meters. The height difference in these two is 9. 9 150s. So you see, the subtraction of these two numbers won't be the same. If I take 1,500 divided by 150, I get 10. If I take these relative numbers and divide, I still get the same answer. This is why we're always encouraging you to simplify numbers. If you're going to take the number 10,000 and divide it by 100, then you can actually take 2 zeros off this number and 2 zeros off that one, and the ratio will not have changed. And this allows you to work with a whole mess of simpler numbers than before. And that's one of the reasons the astronomical unit comes in handy. We shrink the numbers down so they become more manageable. But now we don't talk about meters in height. We talk about, oh, it's 10 times taller than the previous one. And that's why the relative numbers come in really handy. Now let's take a look at the assignment I've created. If you watched my video, this is the summation of it. When we create a relative number, we compare one number to another. So the story goes that when we used to want to visit my parents and my sister down in Windsor, and my daughters would ask me, how far away is Windsor? Well, a little child can't understand 344 kilometers, but Toronto is 82.9 kilometers away. So I could say, by taking 344 divided by 82.9, I get an answer of 4.14. This says Windsor is 4 times further away than Toronto. Another way of phrasing it, if they asked me how long was it going to take to get to Toronto, I would say 2 Max and Ruby's. Because at the time her favorite show was Max and Ruby, so I would just pick a show that the child could use as a benchmark. So we want to see how far away these places are as a Windsor distance. Here's the example for Windsor. You get 4. Toronto is the benchmark. So when we take Toronto's distance and divide it by Toronto's distance, it's 1. So your benchmark one becomes number 1. What happens though when we get Guelph? You're going to do Guelph, insert, I'm thinking. Oh, come on. You have no idea how much I edited out for you guys. Now I'm making you suffer with me. Divide by 82.9. And you lazy bones can do the calculation yourself. Now, the first thing you're going to want to do is type in 82.9 divided by 53.2. Boy, we want to make our divisions equal to larger numbers than 1. Guelph is a fraction of the distance. I can round in my head to 5/8, which gives me 0.625, because I'm just that cool. 0.625 Toronto's away. So each of these numbers here, you're simply going to do this, and you will get your relative scale. Now, once you have these numbers, you're going to want to graph them down here. But I don't want you graphing on this because I have no means of looking at it. So what you're going to do is you're going to delete it, And then you're going to go to Insert, Chart. And you're going to insert a column chart. I'm thinking. And then you can play with this and rearrange it to take these values here. Not here, these ones. Okay? And you're just going to give me a bar chart showing the relative distance. And you're going to encounter a problem here that you can explain to me why this bar chart's going to be hard to make good use out of. There's something that's going to throw you. And you can just explain that to right here when you hit that problem. Now we switch to the solar system. I've already rounded for you. I've already actually done some scaling. The actual distance to the sun to Venus. So Venus from the sun is 108, 1, 2, 3, 4, 5, 6 kilometers. Earth is 1, 2, 3, 4, 5, 6 more as well. Every last one of these numbers here has 6 more zeros on it. I took them away and put them up in the heading because the answers will be the same. If I took 6 numbers off all of these, 6 zeros, then it won't change the division. So we want to find out how much further other planets are compared to Earth. So we set our benchmark. Earth is 150 million kilometers from the sun. That's a benchmark of 1. I'm going to jump up to Saturn. Saturn is 1427 million kilometers away. And I'm going to do this. Got to do it. Change my number. 150. Now, 1427, that's pretty much 1500. Okay? I'm going to round it for you guys. Shut up, dog. So really, it's pretty much this number. And what's that? 10. So Saturn is 10 times further from the sun than Earth is. What about Mercury? What happens when we take Mercury and divide it by 150? Once again, your brain is desperately going to make you want to do 150 divided by 57. Now, again, we're all friends here, so I'm going to take this, and I'm just going to do a little bit of Kentucky rounding here. Here's my Kentucky rounding. 50 divided by 1/3. What ratio is that? Oh, come now. That's 1/3. So we would say Mercury is 1/3 astronomical unit from the sun. Saturn is 10 astronomical units. Earth is 1. So Mercury is 0.33 the distance that Earth is from the sun. Another way of phrasing it is to say, Mercury only has 33% the orbital radius that the Earth does. Ooh. This should be quite easy then. Except for this last one. I'll let you stew on that one. But you get the idea what an astronomical unit is? And then you just have to answer me this. Riddle me this. Okay? So that should be enough to get you through this assignment. And see if you can figure it all out, because it's a good math skill to have.